Imagine treating a brain tumor with a scalpel. Doctors route tiny drug carriers through bloodstream and slip them past the brain's toughest security systems, the blood-brain barrier. The barrier is the reason most cancer drugs never reach the tumor. It's a biological wall, good for defense, bad for therapy. So researchers use a simple trick with serious power: microtubules and focused ultrasound. Here's the move. You inject harmless microtubules into the blood. Then a clinician aims ultrasound at the tumor's blood vessels. The sound makes the bubbles vibrate. The vibrations tugs on the vessel walls and loosens the tightened junctions between cells. For a few minutes, a controlled doorway opens. Not a hole, a temporary gap the body can reseal. Now they send in the nanobots. They're not metal spiders, they're nanoparticles that are lipid spheres, polymers, or tiny magnetic beads carrying chemotherapy. Some have targeting molecules on their surface. Some respond to heat, pH, or enzymes. Imaging guides them. MRI or ultrasound shows the exact region where the barrier is open. Magnetic fields or acoustic pulses can help steer the dose. At the tumor, the cargo releases on cue. Drug concentration rises inside cancer cells while healthy tissues get less exposure. In preclinical studies, delivery has jumped dramatically, sometimes even tenfold. And in early clinical trials, teams already use ultrasound to open the barrier and infuse therapy under strict monitoring. When the treatment window ends, the junctions close and the barrier resets. This approach tackles more than cancer. The same doorway can carry antibodies for Alzheimer's, gene therapy for rare disorders, even enzymes for metabolic diseases. It is targeted medicine at the scale of cells. Risks exist. Too much ultrasound can heat tissue. Bubbles can stress vessels, particles can trigger inflammation. That is why systems use feedback control. Real-time imaging watches the bubbles. If the signal rises, the power drops. Dose, pressure, and duration stay inside safe limits. Most carriers are designed to break down and clear after delivery. The big challenges now are scale and control. Manufacturing consistent particles, tracking billions at once, and proving benefit at large trials. But the blueprint is set. Open the gate, guide the cargo, hit the tumor. The smallest machines are learning to reach the hardest places. Want more mind-bending science? Hit subscribe and stay ahead.